Okay, we'll start. So. Okay. So this is the second last chapter. And it's quite a small chapter. In fact, we'll have it finished this week. And this chapter is also going to be part of your paper as well, your maths assignment. Okay, so it's an important chapter for your assignment. Okay. What's wrong? Oh yeah, the circle one. I forgot about that. Okay, so I'll start off with that. So I think I said you have your circle. Try that again. And then, what did I say? Oh yeah, there's this triangle in it. And we have to show that this angle here is 90. So let's call this O, this A, this B, and then this one here C. So if I want to show that this is 90, basically want to show that CA is perpendicular to CB. CA perpendicular to CB. So to show that, does anybody know what these letters mean, RTP? No? It means I'm required to prove that CA dot CB equals 0. So if I want to show that they're 90, basically I need to show that the dot product between them is 0. So let's start off. CA dot CB, that equals A minus C dot B minus C is A dot B minus A dot C minus C dot B plus C dot C. Now if I look at my triangle there, you can see that B is equal to minus A. Because if you look at it, there's B, which is the same length, but just in the opposite direction of A. So in other words, B equals minus A. So I can replace now my B with minus A. So here I get minus A dot A, minus A dot C, replacing B with minus A here as well, plus C dot A, plus C dot C. Now, this is minus A dot A, minus A dot C, plus A dot C, plus C dot C. Now you can see in the middle two terms cancel. This would be minus magnitude of A squared plus magnitude of C squared. But if you look at this here, there's A and there's C, for example. What's the length of A? Well, it would just be it'd be a half AB, that's true, yeah. But if you look at it as a circle, the A would be the same as just the radius of the circle. It's the same length. And likewise, what would the length of C be? Also the radius. So this here can be replaced by minus R squared plus R squared equals 0. Got it? Yeah? Okay. So we'll start now. So we saw from semester 1 how to solve a quadratic and how to solve a cubic. Do you remember what you need to do to solve a cubic? What do you have to do first? Anyone remember? Long division. And then before even the long division. So you're right, you have to do long division. But what do you need for long division? A factor. So how do you find a factor? You have to guess, right? So that only works if one of the factors is a natural number. If the factor was like 0.5, you've no way of guessing that. So we want to try and find a better way to solve not just cubics, but all different types of equations. So here's the general problem. We have this function. Did I not write on the top? Sorry, I was distracted with the vectors. Newton Raphson method. Yeah, this guy again. Thinks he's so great. Right, so here, the idea is we have this function, y equals f of x, and we want to try and find the roots here. So the way the idea works is first you guess. So for example, when we did in semester 1, our first guess was usually 0 or 1 or whatever, like this. So rather than picking a number, I'll call our first guess x1. This is our first guess. Now if you look at this diagram, you can see that this is definitely not the root because the root is right here. So this is the root. And we're trying to get to there starting from here. And of course we don't know where this is. So what we do is we go up to here, and this point here we can find. This one here will be the point x1, fx1. Then what we do is we find the equation of the tangent at this point. So let's do that. Let's use this x1 and fx1 as our x1, y1. Let's find the equation of the tangent. So we have y equals mx plus c. And as you remember, the m is the derivative, that's the slope of the tangent. So m gets replaced with f derivative x1 plus, x plus c. Now how do you find the c? What do you do? Sub in a point. So we get f x1 equals f derivative x1 plus c. So we end up with c equals f x1 minus f derivative x1. Now I know it looks difficult, it's only because there's no numbers in it. We're just doing equation of the tangent here. So we end up with this equation for the tangent. Y equals m x plus c. Come back for the next class. Okay. Now if you were to look at the, don't worry, I'll zoom back out now, but just to go back to this graph for a moment. If you were to look at this graph, if you start at x1, and remember you don't know where the root is, but you've just found the equation of this tangent line, you notice that if you find the root of the tangent line, which is right here, that would be closer to the true answer, right? And imagine that you repeated the process. If you went straight up again and drew another tangent line and found the root of that tangent line, you see again it would be even closer. So what is the root of this tangent line? Well, you just put y equal to 0. So y equals 0. And I'll call the solution x2. So I'll replace x here with x2. So taking everything to the left, I get f derivative x1 minus f x1 equals f derivative x1 x2. So now finishing by just dividing there by that derivative, x2 equals x1 minus f x1 over f derivative x1. And that's really the key result I'm getting at here. So what you have here is x1 is a point where you start at, any point you like, and then x2 is an improvement. It's a closer value to the true root than x1 was. So you think to yourself, well, if I did this formula again, then I get an even better approximation. So likewise you can say x3 equals x2 minus f x2 over f derivative x2, and so on and so on. So in general you can write the formula like this: the next estimation of the root is equal to the current estimation minus f xn over f derivative xn, and this is called Newton-Raphson's formula or method. What's the name of this type of sequence from semester 1? No. No. Not geometric, not arithmetic, not convergent, divergent, periodic. What type of sequence is this? Recursive, maybe? Remember this word? Yes. So this is a recursive sequence because the next term gets fed back in. So I'll give you an example of this, one where we know the answer. By the way, notice how the function is in the numerator, because when you arrive at the root, this will now be 0 because you're at the root, meaning that there's no more change. So if we want to think about it like this, the improvement is equal to what you guess, and then plus this change thing here. You know, this is the part that's making it change. This is what's getting added on. So this piece here will get smaller and smaller as you get closer and closer. So let's have a look at an example. We know the answer here. What do you need for x to make this equal to 0? 1. So we know the answer. So let's see the method work, okay? So for example, we try and start with x1 equal to, let's say, any number. Let's say we're way away from the answer. Let's say x1 is equal to 10. So we know the answer is 1. So if we were doing this bit by bit, we would then try 10, then 9, then 8, then 7, then 6, then 5, and so on. So if the answer is very far away, it would take a long time. So let's see what the next value would be. So the rule is x2 is equal to 10 minus f of 10 over f derivative of 10. Now I should write down what the derivative is. So that will equal 10 minus 99 over 20. Now can somebody type that in, please? I think I did that right. 20. What is it? 5.25? No, give me the whole thing, please. Yeah, what is it? 5.05. Okay. x3, that would be 5.05 minus f of 5.05 over f derivative 5.05. So that would equal 5.05 minus, then big brackets here, 5.05 squared minus 1 over 10.10, because it's 2x. So can somebody type that in, please, and tell me what you get? 2.62. Okay, so the next one, x4, would equal 2.62 minus 2 times 2.62, and then 2.62 squared minus 1. Okay, so what would that be? And I'll do one more now, 1.5. Okay, so then x5 would be 1.5 minus 1.5 squared minus 1 over 3. 1.1, okay. So if you were to look at our numbers, we started off with 10. Then what was the next one? 5.05, 2.62, 1.5, 1.1, and I guess if we do the next one, it'd probably be something like 1.01, I'm guessing. So you can see that this method, it really moves in quickly to the answer. At the beginning, it's taking big steps, and then as you get closer to the answer, it starts to take smaller steps as it moves into the answer. So we'll have a look at another example now. Okay. So let's say fx equals x cubed minus 8. Now what some people like to do before they start this is to simplify the formula. So the formula is xn plus 1 equals xn minus fxn over f derivative xn. So that would be xn minus x cubed minus 8 all over 3x squared, n and n. So xn plus 1 for this one, if you wanted to write it out, it'd be xn, will I put the minus in? Yeah. Plus over 3xn squared, 8 minus xn cubed. Yeah.
It's supposed to be plus.
I put the...
okay.
Yeah. Right, so, can you see what the answer is here? Well, it doesn't matter if you can't. So let's start with any number and see what we end up with. So let's start with x1 equals 1. Then x2 would equal 1 plus 8 minus 1 over 3. So that'd be, what's that? 1 plus 7 over 3. Yeah? That's 10 over 3? 3.33? Is that right? Do you have calculators? Check please for me. No. Keep up. Sorry. I need to move ahead. Yes? Okay. x3 equals 1 plus 8 minus 3.33 cubed over 3 times 3.33 squared. What's that equal to? It is, what did you say it was?
0.13.
No, I think you typed it in wrong. I got 0.46. Sorry. x4 would equal 2.08. x5 would equal 2.003. And then x6 would equal 2.000005. So what do you think the answer here is moving towards? Yeah. X, the root, will equal 2. Which of course if you look back at the question, yeah, 2 cubed minus 8 is 0. Remember I showed you a quick way to do these recursive sequences in semester 1 on the calculator. Now, there's a couple of drawbacks with this method. Can anybody see one major drawback with this method? Any ideas? Like what's one problem with this method? Something maybe you've noticed? No? How many solutions does a cubic have? 3. And in this case, how many did I find? How many solutions did I find here? No, these aren't 6 solutions. This is just me moving towards one solution. So one big problem with this method is that it'll only give you one answer, even if there's more than one answer. This should remind you of something in derived class last semester, where I said there was a method in derive where if you couldn't find the answer, it'll give you an approximate answer, but it'll only give you one answer. Yeah, that's actually what's happening. It's using a process like this to find the answer. So one drawback, if I want to list down drawbacks, number one, there's only one answer. Any other problems? Any other problems? No? No potential problems? Let me help you out a little bit. Look back at the formula. Any problems you could have with this formula? I give you a clue. Look at the denominator. Yeah, what could be? There's a problem if the derivative is 0. So if the derivative is 0, then you can't go any further because you've broken it. So if you want to put it like this, you break it if you land on a turning point. So if you accidentally land on a turning point, well then it's broken, because you can't go any further because your derivative, you're dividing by 0 then. So it's a big problem. And then the third problem is you've no guarantee that this will get you to an answer. The examples I did work, and most of the time it works, but you've no guarantee that it will go towards an answer. It could just move away to infinity or minus infinity. So it may not converge. So in all my examples it was convergent to the answer, but you've no guarantee that it'll converge. I just can't see, think of an example. I'll find you I'll find you an example where it doesn't work in number 3, but that wouldn't happen in the exam anyways. Of course, they'd only give you one where it does work.
Is that it?
What do you mean, is that the 3 problems?
No. Number 3, what's the beginning? Is it 1 plus?
Oh, it may not converge. Yeah, no, sorry, not 1 plus may not converge. Okay. Yes.
Could you please explain what convergence is?
No, this is from semester 1. Sorry. You'll have to look it up. You have your notebook. The one titled possibly Convergence or Convergent, maybe, I don't know. It was from Sequence and Series. Yes? Now, before we go ahead, we need to check, how can we check that something has a solution? So one simple way to check is you notice that if you go from a negative to a positive, that there must be some solution in between. So for example, if you have fx equals x squared minus 1. So what's f of 5, for example? Well, that would be 24. Yeah? And then what's f of 0? Minus 1. So if you were to draw this graph, at 0 you're at minus 1, and at 5 you're at 24. So if you want to show that this has a solution, what you need to do is pick 2 points and see if one is positive as one is negative. And if that is the case, then there must be a solution in between. So I can say Since f of x changes signs, so in this case I went from negative to positive, from 0 to 5 is negative to positive, then that means there's a root somewhere between 0 and 5. So if you want to show that something has a root, all you need to do is show that it changed its sign going from one location to another location. Now, this doesn't always work, and you can see why in this example maybe. fx equals 1 over x. So what's f of minus 1? What would be f of minus 1? Minus 1. And then f of 1 would be 1. But, yeah. Yeah. But this does not have a solution between minus 1 and 1. And the key difference between this and my last example, well, what is the problem with this function? What makes it so different to the last one I did? No, that's fine. Say again? F of 0 is not 0. Yeah, which is a problem. You see, this only works if the function is continuous, if it's not broken. Here, this is broken. Where is it broken? It's broken at x is 0. So you can't use this for examples which is broken like this. You can only use it when it is what we say continuous, when it's unbroken. And again, in the exam, that will always be the case. So for example, another one, if I want to show that fx equals x cubed minus 8, I want to show that this has a root. So f1, what would that equal? Minus 7. f3, what would that equal? What's f3 here? Well, it would be 3 cubed, which is 27, minus 8, so that's 19. So fx changes sign from 1 to 3, therefore there's a root somewhere between 1 and 3. Now in the exam, it's a nice little question that they give you in section A. They give you this, and they give you the 1, and they give you the 3. So actually all you need to do is calculate f1, f3, and then make this statement, and you've got your marks. So this will be given to you, and the 1 will be given, and the 3 will be given. The question would say something like, show this f of x function has a root between 1 and 3. Be something like this. Okay. So the next thing is we just want to, something small, check how many roots a cubic has. So you know a cubic usually has 3 roots, but it sometimes has 2 and it sometimes has 1. So we just want a quick way to check how many roots it has. So we'll give you an example here. Let's say y equals minus 10x cubed plus 3x squared plus 37x minus 18. So the way to find out how many roots a cubic has is you should do a very, very quick sketch, and you should include the turning points on the sketch. So the derivative here, minus 30x squared plus 6x plus 37 equals 0. So I can see that this one here has two roots. The first one is at minus 1 point something. So I'll just put in minus 1 roughly. And then the second one is at 1.2 roughly. So I'll just put in 1.2. Okay. Also, you know that when x is 0, what's y? Minus 18. Now be careful, these are turning points, not roots. So I need to put these values in here to get the y's. So minus 10, 1 cubed, plus 3 times 1 squared, plus 37 times 1, minus 18. So the first one would be up at 12, so that'd be here. And then changing that to 1, sorry, no it's not, don't write down the 12, I didn't put in minus 1. It'd be minus 42, so that's way down here. And then the second one is 1.2, okay. 1.2, 1.2, 1.2, 1.2. So at 1.2 you get 13 about. So that'd be there. So the first point is here, there's one up there, and then there's one here. Okay. So if I was to draw this, do you remember minus? What shape a minus cubic makes? Does this go up or does it go down? It goes down, doesn't it? It goes down, and then this is a turning point, and then this is another turning point. So we'll have to go down to here, and turns here. This is a turning point. Then goes up here, and it just passes through here because I just got that one by putting x is 0. And then what happens when it hits this one? It's a turning point again, so it has to turn again. And it's like this. So how many roots would this have? It would have 3. Now, what would happen if this turning point was underneath the x-axis? How many roots would it have then? No, it would just have 1, because it would go down, it would go up, and then it hits this turning point and goes back down. So the only time it crossed the x-axis was here at the beginning. So what situation then would I need for it to have 2 roots? So here is 3 roots, and then we put in, as an example, red. If the turning point was down here, then that would be 1 root. So what would I need for it to have 2 roots?
When it's 0. When it's at 0.
When's what at 0? The turning point, yeah. So if this turning point was on the x-axis, then what would happen? It would go down, turn, pass through here, and then turn when it hits the x-axis. So then this makes it have 2 roots. So you can tell how many roots it has by really looking at where the turning points are. Okay. Okay, so the last thing to show you with this now, the last thing to show you is why it's important to have as small of a gap when you're trying to prove that there's a root at the beginning. So I'll give you a small example. Sorry, I have to go down now. So let's say fx again equals x cubed minus 8. So we said f0 equals minus 8, and f3 is 19. So therefore there's a root somewhere between 0 and 3. Okay, now what about if I did it like this? Fx equals x cubed minus 8. So if I said f1, that would equal minus 7. f3 would equal 19. So I get the same result. There's a root somewhere between, but this time it's between 1 and 3. So which situation do you think is better, the first or the second? Which one is a little bit better? Like if I told you that there was an answer between 0 and 3, and then I could have told you there was an answer between 1 and 3, which is better for you to know? 1 and 3, because there's a smaller possibility. In the first case it's somewhere between 0 and 3, in the second case it's somewhere between 1 and 3. And then you could take it to even more extremes. So you could end up saying, I think f of 1.9 will be negative, f of 2.1 will be positive. So you could end up saying there's a root between 1.9 and 2.1. So basically the smaller the interval is, the better. So before you start the problem, you could work out how many steps you would need to use the Newton-Raphson formula for. So here's what you might call number of steps. So before you start a problem, if you need to know how many steps you need to take, it's equal to log base 2, and this delta L thing here, that means how big your interval is at the start. So for example, in my first one, it would be 3 minus 1, so it'd be 2. The first one here, 3 minus 0 would be 3. This is 3 units long. This one here is 2 units long. And then this one here is 0.2 units long. So it's log base 2 divided by 10, and then to the power of how many decimal places you want your answer to be accurate to. So example, fx equals x cubed minus 8, and we know there's a root somewhere between 1 and 3. And I want this answer to be accurate to 2 decimal places. So how many times do I need to use my formula? Yeah, huh? We'll see. Log base 2. What's delta L here? How big is this interval? 2 units long. And then it's 10 to the power of 2, because you want the answer to 2 decimal places. So let's see what this is. Log base 2, 2 over 10 power 2. Oh, sorry, there's also a minus in front here. So I got 5.6. Yeah, but I forgot to put the minus in front of my formula. So I got 5.6. So you have to round that up to 6. So what does that mean? That means by the time you get to x6 in your formula, you will be at the right answer to an accuracy of 2 decimal places. So x6 will be the root to 2 decimal places.
How do you know it's still x6? How did you know it's
Because I got 6 steps as my answer. I'll have to use my formula 6 times.
delta L is 3 minus 1, right?
Yeah, it's the length of the interval of where the answer could lie.
Shall you
Scroll, I'll zoom out. Sorry, I didn't have the minus in the formula to begin with. There should have been a minus there.
It's always the second root minus the first root.
The end minus the start. Okay. That very last thing I showed you there about the number of steps, it's probably not on the exam. I mean, well, it will be on the exam, but they won't expect you to do it that way, okay? What they'll expect in the exam is you keep using the formula until you notice it's not changing anymore to 2 decimal places. But if you want, you can use this formula before you start the question to check the absolute maximum number of times you should be using the formula. But I often find in the exam, I've never seen them ask you a question that needs the formula more than 3 times. So 6 actually is an extreme example here. But if you wanted to check before you started the question, how many times do you need to use this formula to get to the answer, you can use this formula here for the number of steps, okay? But like I said, if you're doing it more than 3, you're probably doing something wrong in your calculator. Sorry. Right, I'll give you these questions now to try.